Hey guys, welcome to Unit 9 Notes B. Today we're going to talk about calorimetry. In calorimetry, we're interested in an experiment that's going to help us indirectly measure the heat involved in a process. I want to start off with a quick question. Say you leave your keys in your car and your chemistry book in your car. Which one do you think is going to feel hotter when you go to take them out of the car? Well, when you pick up the metal, it might burn you. It's getting hotter. It feels hotter. But when you go to touch the chemistry book, not so much. It's the same idea as how the seatbelt, the metal part of the seatbelt, can burn you when you put it on. That metal is going to feel hotter than something that has a higher specific heat, like the textbook. So it all has to do with the specific heat of an object. If the specific heat is low, such as with a metal, you're going to be able to conduct heat more quickly. Whereas if you're touching something that is not made of metal, something made of something with a higher specific heat, like paper, or the cloth seats of your car, that's not going to be as effective at transmitting heat or less thermoconductivity because it has a higher specific heat. So it all has to do with the specific heat of a substance, and every substance has a unique specific heat. So to recap this very important definition, the specific heat is the amount of energy it takes to raise 1 gram of a substance 1 degree Celsius. The more energy required, the higher the specific heat. So let's look at a specific example. Say we want to melt an ice cube. How much heat would it take to melt that ice cube? Well, we learned a formula for calculating the amount of heat, right? Q equals mc delta T. Well, that might be good for some situations. It doesn't really help us with a phase change because we know that the temperature does not change during a physical change like these phase change, or I should say just does not change during a phase change. So because I know the temperature doesn't change, would I be able to really use this formula? Picture putting in delta T here. When you multiply by 0, what happens? Well, your answer is 0. But I know that it's not true that it takes no heat to heat an ice cube, to melt an ice cube. Melting does require heat to break the intermolecular forces. So how can I determine how much heat if I can't use Q equals mc delta T? What would be the solution? Well, that's our experiment here, calorimetry. So to add some definitions to this real quick, melting is a process that requires a certain amount of heat, and that heat has a special name, the latent heat of fusion. Latent basically means hidden, so it's not very obvious that there's heat involved since there's no temperature change. And heat of fusion is going to be referring to like bringing those particles more close together, kind of strengthening those intermolecular forces. So the amount of heat required for melting is known as the heat of fusion. So calorimetry is going to allow us to indirectly measure that heat of fusion. On another quick side note, I want to point out the use of the word indirectly as opposed to the word inverse. Those get mixed up a lot by students. When I'm talking about inverse, I'm talking about one variable increasing while the other is decreasing. That's an inverse relationship, not an indirect relationship. Indirect means I'm looking at the effect of system A on system B, and then I'm able to use that effect to make some inferences about system A. So I can't measure A directly. I'm going to measure A's effect on B and be able to infer indirectly what caused those effects. So calorimetry is basically going to allow us to measure how much heat is being produced or absorbed by one thing. Some specific examples, maybe a chemical reaction occurring, maybe a change of state, which would be your phase change, or even forming a solution. You may remember the heat of solution from Unit 8, which was the heat needed to dissociate in the first step of dissolution. So we can look at how much heat is given off or absorbed by these substances, by these reactions, by these phase changes, even when they can't be measured directly. And we can do that by looking at their effect on something else, namely water. So this is an experiment, so we want to kind of emphasize one thing that's important to control during an experiment that is focused on temperature, and that would be pressure. And pressure is not as hard to control as you would think. It's mostly relatively dependent on altitude, so as long as I don't magically move my experiment to like the top of Mount Everest or the bottom of the deep blue sea, we should be fine to be at constant pressure. The device used to perform calorimetry is known as a calorimeter, and your challenge for the lab is going to be to design an effective calorimeter. Theoretically, a calorimeter should ensure that the heat transfer is only going back and forth between the water and the system we're trying to test. So let's look at an example of a calorimeter. This is a very simple version. We call it a coffee cup calorimeter. Picture a styrofoam coffee cup. Styrofoam would be insulated, and being a bad conductor of heat, that's really important. Very good insulator so that the heat is focused inside of the cup. The idea here is to keep the transfer between our ice cube and the water that's around. So we would call the system the ice. That would be the ice, the thing we're trying to dissolve, or the reaction that's happening. Whatever it is that I'm trying to indirectly find the heat of is our system. And we want to make sure that the transfer is only between the system and the surroundings being the water. So we want to try to minimize heat being lost to the air or to other parts of the calorimeter. We want that heat transfer theoretically to only be between the ice and the water, or more generically speaking, between the reaction and the calorimeter. So we want to improve this design and try to think of some other ways to insulate this heat. So we may want to put something like a lid on top. We may want to use a stir to make sure that the thermometer is getting a uniform reading and there's not hot pockets and cold pockets. There's lots of ways to improve our calorimeter, and that's your challenge for the lab. What are some other things that you can do to ensure that the heat transfer is only between the item that we're trying to find the heat of and the water? So food for thought. Let's go ahead and look at what happens inside the calorimeter. One object will always lose heat, where the other object will always absorb heat. So let's bring in those words exothermic and endothermic again. The exothermic thing will be the thing losing heat, where the endothermic thing would be absorbing heat. And again, you need to know your signs. Endothermic is always a positive Q, and exothermic is always a negative Q. So in the example of the ice and the water, the ice needs to absorb heat in order to melt, and it's going to get that heat from the water. So the water would be losing heat, being exothermic, and the ice would be absorbing heat, being endothermic. Let's look at another example. Say we have a hot piece of metal, and we are going to put that into a cold glass of water, inside of a calorimeter, I should say. As the hot metal loses heat, that heat is going to be emitted out into the water. So what's exothermic in that situation? The metal that's losing heat, making the water endothermic as it's absorbing heat. So one thing is always losing, one thing is always gaining. This is due to a very important law, known as the law of conservation of energy. The heat will always flow from hot to cold, and the magnitude must be the same. So can the metal lose more heat than the water gained, or vice versa? No. In theory, the magnitude or amount of heat exchange should be equal. Heat lost must equal heat gain due to the law of conservation of energy. Notice it does say magnitude, so the gain would always be positive and the loss would always be negative, because endothermic is positive and exothermic is negative. So if this is like a positive 5 joules, the heat lost would have to be a negative 5 joules. So there is a sign change, but the number of the heat loss or heat gain is the same. All right, so when we do problems, we can actually use a little chart to organize these word problems. They're going to start to get a little bit big. And this chart is really handy for making connections, such as the heat magnitude needing to be the same. So to set up this chart, you're going to just use your Q equals MC delta T formula down the side. QMC. And then for delta T, I always do final over initial. This is going to set it up for you to be able to just straight subtract. And you can even write your delta T right under your chart here. As you plug in numbers, you're going to notice that the Q for the calorimeter and the Q for the object or the reaction, the thing that you put in the calorimeter, these should be the same in number. But you're going to have the positive on the endothermic part and the negative on the exothermic part. One other thing to note here is the final temperature for both substances would have to be the same, because heat always flows from hot to cold. So when would the heat stop flowing? When would it end or finalize? Once those two temperatures are the same and neither one is hotter or colder than the other. So our final temperatures will be exactly the same and our heat will be the same number but with the opposite sign. So this chart's going to allow us to employ these different laws and theories to actually solve the problem. So let's actually look at a problem. We're going to start plugging in some numbers using our chart. So we always want to set up our chart. Q equals MC, and then delta T is T final minus T initial, so that we can get our delta T. So, starting from the top, a small pebble is heated and placed in the foam cup calorimeter. So notice our two columns. We have the water, which will always be what you're putting in the calorimeter, and then the object will change. Maybe we're putting an ice cube, in this case a pebble, it could be a reaction or something to dissolve. This is the thing we're trying to indirectly solve for. So it's going to be placed in a calorimeter that contains 25 grams of water. So grams we know measures mass, but we've also got to be careful that we put it in the right column. That says that's the mass of water, so it's going to go right here, 25.0 grams. And it says that that is at 25 degrees Celsius. So notice it's still talking about the water, so I'm still in this first column. I've also got to consider whether it's the final or the initial. So because this is the beginning, because I haven't started the experiment yet, I would assume that's the initial temperature. So that's going to go in the bottom of this column, 25.0 degrees Celsius. Then it says the water reaches a maximum temperature. So this is important, especially in theory as we go into the lab. The maximum temperature is going to be what you reach once the temperatures are the same. After the temperatures reach the same temperature, their final temperature, the heat will start to decrease, but that's going to be because your calorimeter is basically failing. The heat is starting to emit from the sides instead of just transferring between the system and the surroundings. So our maximum temperature basically always means our final temperature. So that's going to be 26.4 degrees Celsius. The question is, which column do I put it in? And the catch is, if it's the final temperature, it applies to both columns. Otherwise, it wouldn't be the final temperature. So I'm going to go ahead and get in the habit of writing that in both columns. 26.4 degrees Celsius. Okay, next question. How many joules of heat? So I found my question mark. But am I looking for the heat of the water or the heat of the pebble? Released by the pebble. So I am trying to solve for the Q of the pebble, the Q in my second column. Right now, I only have enough information to start on my first column. Our goal here is going to be able to find the Q of the water, and then I can find the Q of the pebble because I know it should be equal in magnitude, but have the opposite sign. Before I go ahead and start solving with Q equals MC delta T, I'm going to go ahead, because I like the way this table is set up, and go ahead and find the delta T. The TF of 26.4 minus the TI of 25.0 is going to just be 1.4 degrees Celsius, allowing me to get my change in temperature. So I like to do that so that once I solve with my final and initial, I have my delta T, and that way you don't have to worry about system of equations. We can just plug in MC delta T, multiply them out, and find our Q. So let's go ahead and set this up in the calculator. All right, here we go. Oops. Table's much higher. There we go. So we found our mass, our specific heat, and our delta T. So I can multiply these together to get the Q for the calorimeter by multiplying the mass of the water, specific heat of the water, and the delta T of the water. So we've got 25 times the 4 times the 1.4, and we get Q for the calorimeter of a positive 150 joules. Again, the delta T usually dictates, or always dictates, the sign of the Q. So because I had a positive delta T, the water was absorbing energy, I have a positive Q. So now for the pebble, it's going to be the same number, 150 joules. But where the water was endothermic, the pebble would be exothermic, which makes sense to the question, right? It said the pebble was releasing energy, how much energy was released. So if you're writing this as a Q, you want to make sure that you include the negative sign. If you're writing this in words, you would want to make sure that you're using the word released. I need to know that you understand it's exothermic. So you can't just give me 150. I need to know whether it's absorbing or gaining, whether it's positive or negative. All right, and it is 2 sig figs, by the way, because of our delta T, the 1.4. So it is 150 or negative 150 joules. All right, let's look at another question. This example is actually exactly like what you're going to do in the lab. So I'm going to go through and identify my variables and try to put them in the chart. I have 100 grams of water at 22.4 degrees Celsius. So grams I know would be my mass, and because it's in water, it's going to go in the first column. This 22.4 degrees Celsius seems to apply directly to the water, but the question is it the final temperature or the initial temperature? Well, it's at the beginning of the experiment, so that would be the initial temperature. Next, I have my 75.25 grams for aluminum. Now, since I know the mass is of the metal must be what I'm trying to find. So instead of my last column being for the pebble, this time I'm going to make my last column for aluminum. What we're going to do next is a little bit different. We're going to actually need to heat up the metal in order for it to be able to release energy. We looked at the example earlier, like what if you put a hot chunk of metal in a calorimeter, which would be exothermic, which would be endothermic? Well, it's got to get hot somehow, right? So that's also an indirect process. What we're going to do is put the metal in boiling water. We're going to heat up the metals for like 5 minutes while it's in that boiling water. So by the time that we take it out, the boiling water, which is about 100 degrees Celsius, right, would be the same temperature of the metal as I start the experiment. So this would actually be the temperature that the metal or the aluminum is starting at. And then it reaches eventually a final temperature, which we know will apply to both substances, our final or maximum temperature of 32.9 degrees Celsius. The specific heat of water is something that you'll always be using, so it's a good thing to know, because we're going to be plugging that in on this for the specific heat of the left. It might be tempting to just look up the specific heat of the aluminum, but we are trying to experimentally determine the specific heat of aluminum. And we are going to get a number that's slightly different from the book value. And from there, you can find your percent error. So how would we find the experimental specific heat of the aluminum? Let's go ahead and show those numbers that we just talked about plugged in our chart. So we had our 100 grams of water as the mass of water. We had the 22.4 degrees Celsius as our initial temperature of the water. We had our 75.25 grams as our mass of the metal, 75.25. We have the initial temperature of the metal as the 99.3 degrees Celsius. In your experiment, make sure that you actually find the temperature, because it's not going to be 100 on the nose. It's going to be close to 100. Water is supposed to boil at 100 degrees Celsius, but measure what it actually is. And then we've got our final temperature of the 32.9 degrees Celsius. So we have enough information on the left to solve for the Q of the calorimeter, and that's the first thing we should do. Then from here, we can flip the sign to go from the heat of the water to the heat of the aluminum, because I know that these should be equal in magnitude, but opposite in sign. Then I have everything except for the specific heat of the metal. So then I'll be able to use Q equals MC delta T down the other side. So this is essentially a three-step process. Before I begin the actual calculation, I like to go ahead and use T final and T initial to solve for delta T, so I don't have to worry about a system of equations. So 32.9 minus 22.4 first. And my delta T is 10.5 degrees Celsius. So notice I have one decimal place and I'm subtracting, so I'm going to keep my one decimal place. Now watch your sign here. We're going to do 32 minus the 99. 32.9 minus 99.3. And we get negative 66.4. Once I find my delta T, I like to cross these out so I don't get confused plugging stuff in. I have my delta T, my C, and my mass. So now I can solve for the Q, flip the sign, and then solve down for my specific heat. Oops, missed my degrees Celsius. All right, so that's our plan. We've got our chart. We're going to plug this in. make your chart, calculate for Q, flip the sign, calculate for C. All right, so first plugging in down the side here, we've got our mass of 100, the specific heat of the water, and then the 10.5, the delta T from our water side. So we get the Q of the calorimeter to be a positive 4,393.2 joules, which should be rounded to 3 sig figs, but it's not our final answer, so it's okay to wait till the end. Then we've got to flip the sign here. We know that the magnitude will be the same, except for the heat of the metal is decreasing. So it's going to be a negative 4,393.2 joules. Same number, opposite sign. Now that I have that, I can solve down for the specific heat, where I would plug in the Q of the reaction, the negative 4,000 on the left, the mass of the metal of 75, and the delta T that we found before, the negative 66. So I would have the negative Q and the negative temperature in order to get the positive specific heat. So when we actually work this out in the calculator, we get a specific heat of 0.879 joules per gram degree Celsius. That's not actually the book value for the specific heat of aluminum. It's actually 0.9. So why would this be a little bit different in a lab? Well, labs have sources of error, right? So what could you use to figure out how accurate your experiment actually was if this is what you came up with? Well, you would want to find the percent error, the difference between 0.9 and the 0.879, and then divide that by your 0.9, and you can get your percent error, or multiply by 100, and you get your percent error. All right, let's move on to a different type of calorimetry. Say you want to find the heat of combustion, something that produces a lot of heat energy. Do you really think you could find the heat of combustion, magnesium reacting with oxygen, producing this super hot flame in a styrofoam coffee cup? Odds are that coffee cup would melt and that would be the end of your experiment. We're going to need something a little sturdier, something that looks a little more like this. The idea here is that you would load your sample that you want to combust into the chamber. You lower the chamber down into the balm calorimeter, and then you're going to be able to take your readings on a display like this. Let's take a closer look at that part. So a balm calorimeter is similar to a regular calorimeter in the sense that it has an insulated outside. It's actually called the door. This would kind of represent your styrofoam coffee cup. It's still got your stir and your thermometer because we want to be able to take temperature readings that are uniform. The difference is now you're going to have the balm inside that actually contains oxygen needed for combustion. The sample will have to go in this oxygen-rich environment down under the water, and then there needs to be something to ignite it. Electricity ran to the outside. So the idea here is that the water is not the only thing absorbing the energy. This is actually going to make the calculation a little more complicated in theory, but not in reality, because what we're going to be able to do is find the specific heat and mass of everything involved and use something called the heat capacity for the entire calorimeter. So that's going to kind of take the place of the MC in the formula. You're going to be able to use the heat capacity of the entire calorimeter instead of the separate masses and specific heats of the water and everything else involved here. So the formula looks something like this. Instead of QMC delta T with the lowercase c, the M and C for just water is replaced by capital C, representing the heat capacity as opposed to specific heat. Heat capacity, capital C. And that's going to be for the entire calorimeter, and you're just going to need to multiply that by your change in temperature to get your heat of the calorimeter. So let's look at one of these types of problems. All right, so this is a reaction between hydrogen and chlorine gas to form a hydrochloric acid. We're doing this in the balm calorimeter. So when we set up our table, instead of using Q equals MC delta T, the M and the C are replaced by capital C. But I can still have a final temperature minus the initial temperature to get my delta T. So it says I have a 1 gram sample, which would be the mass of the reaction, but notice that I don't have a place for the mass. As it turns out, I don't need that number, 1 gram. It's going to react completely as the temperature changes from 20 degrees Celsius to 29.2 degrees Celsius. So these are my two temperatures. The question is which one's the final and which one's the initial. So the final temperature would be what it ends on, the 29.82 degrees Celsius, whereas the initial temperature would be what it starts at, the 20.00 degrees Celsius. And yes, it will be true that the final temperature is the same. You'll see in a minute, we're not going to be able to come down this other side of the column, this second column, I should say, because there's no such thing as the specific, of the heat capacity of anything other than the calorimeter. So these questions are actually a little bit more simple in the fact that this is as far as we can go for the final answer. So we don't really need anything down here, actually. So let's see what else we have in the question. Heat capacity of the calorimeter is given as 9.33 kilojoules per degree Celsius. Look at the units as well. Notice mass isn't a factor. This is kilojoules per degree Celsius. How much energy is required to raise the temperature of the entire calorimeter 1 degree Celsius? So that's what I'm going to plug in here for heat capacity, or capital C. 9.33 kilojoules per degree Celsius. Let's go ahead and find our delta T, kind of finish up our table. Notice the significant figures on this one. We have 2 decimal places each. So because we're subtracting, we're going to stick with 2 decimal places. So it is 29.82 minus the 20, 9.82 degrees Celsius. So now I want to set up Q equals C of the calorimeter, the whole total heat capacity, times the change in temperature. So I'm solving for Q. And I'm plugging in the heat capacity of 9.33 kilojoules per degree Celsius. And I'm going to use the delta T that I found over here from subtraction of 9.82. Notice the degrees Celsius cancels, leaving my units in kilojoules. Be careful that your unit that you're given the heat capacity of is what you end up with for your final answer. And if they asked for joules, we would have to convert kilojoules to joules. They don't happen to specify in this equation or this question, so I'm just going to leave it in kilojoules. Now I'm able to multiply these together and get the Q. The catch is I used the calorimeter's heat capacity and the calorimeter's change in temperature. So that will be the Q for the first column. The question's asking me for the heat of the reaction, which is the second column. So the relationship between these 2 boxes, the first Q box in both columns, is the same as it was with regular calorimetry. It's equal in magnitude, but opposite in sign. So let's see what we get when we calculate this one. All right, so the calorimeter comes out to be a positive 91.6 kilojoules, meaning the heat of my reaction would be a negative 91.6 kilojoules. So the heat must be evolved in the reaction, or we would call this an exothermic reaction. Again, when you give your answer as Q, make sure that you include the positive sign or the negative sign. Notice that that's where it ends. We're not going to go down this column. So we're just needing to find the Q of the first column and flip the sign. Let's see, one last question that has a little bit of a hiccup in it. So first sentence gives me some interesting information. 1 mole of caffeine molecule, is burned and it evolves 4.96 times 10 to the 3rd kilojoules. That doesn't seem to fit anywhere in my table, so I'm just going to jot it down to the side. 1 mole equals 4.96 times 10 to the 3rd kilojoules. But whenever I'm dealing with heat, I have to figure out the sign. So because it says it's evolved, would that make positive or negative heat energy? Evolved means exothermic, so it's a negative amount of energy that would be evolved for 1 mole of caffeine. If we put 1 mole of caffeine in the calorimeter, that number would go right here. But here's the catch. It actually says we've put 5 grams of caffeine in the calorimeter. So we want the heat for 5 grams in here. It's written out 5, which would mean exactly 5. So I'm just going to write 5, and then it will not limit my sig figs. 5 grams is equal to how many kilojoules of energy? So this should look a little bit like a proportion to you, but there are some things we need to clean up. If I know an amount of stuff is this much energy, I can find a different amount of stuff to that much energy. Sounding proportional? The problem is when you use proportions, you have to have the same units. So I need mole and gram to be the same. And it doesn't matter whether you convert them both to moles or both to grams. It's your molar mass conversion, but you're going to have to convert one or the other. Setting up our proportion. So the easiest thing I think would be to use the molar mass of the caffeine, since I know 1 mole is equal to the molar mass, and plug that in as grams. So 194 is the molar mass, so 1 mole would be equal to 194 grams of the caffeine, proportional to a negative 4.96 times 10 to the 3rd kilojoules. So now I want to know how much energy for the 5 grams. So now we're just going to crisscross and solve for x, and we get negative 128 kilojoules. Now that I've solved for how much energy for 5 grams, I can plug that in to my reaction. Negative 128 kilojoules. As soon as I have a Q, I can go ahead and find the other Q, because I know it's going to be the same number, 128, but if the reaction is losing energy, the calorimeter is going to have to gain it. So that's going to be a positive 128. Let's not forget our units here, kilojoules. What else does it give us in the question? The temperature is observed to increase by 11.37 degrees Celsius. So that's my delta T, 11.37 degrees Celsius. But is that a positive temperature change or a negative temperature change? Well, since it says increase, it's going to be positive. So positive delta T and positive Q. Now I just need to plug all this in and find my actual heat capacity. So using Q equals C delta T, capital C, I can then solve for my heat capacity. So to isolate C here, we're going to divide by the 11.37. So we get 11.3 kilojoules per degree Celsius. Notice how the units would work out here too. Joules divided by degree Celsius. And that's why heat capacity is given as energy per degree Celsius. So it would take 11.3 kilojoules to raise the temperature of this calorimeter 1 degree Celsius. If you wanted to work it in joules, you can, or if it asked for it in joules, actually it does ask for it in joules per degree Celsius. So we're multiplying by 1,000 here. And so as in joules per degree Celsius, it would be 11,300 joules per degree Celsius. All right, so that's how we solve our bomb calorimeter problems. The problem you have to watch out for with the bomb calorimeter questions is that they may give you a different amount of stuff in the calorimeter than they give you the energy of. And the fix is just to use a proportion. Once you have the actual energy of the substance, you can plug that in and start reverse engineering your heat capacity. All right, guys, that's going to wrap up everything on calorimetry. This awesome experiment we're going to do together. The next set of notes that you're looking for will be note C on thermochemical equations and some rules and laws of thermodynamics. So we'll see you there.